All right, testing my mic here. Okay, that sounds good. All right, let's get started with this. Let me switch to my overlay here. And there we go. We are officially live. Welcome back to my stream. I think this is the most late session that I've ever done yet. And yeah, here we go. We are on day 11 of Pytorch course, and let's see what new things we learn today. Yeah, without any further introductory jargon, I'm gonna begin. All right. So let's load the video here. So yesterday's Pytorch session, rather I should say, because we're doing a web development session too. We got stuck with a problem. And a majority of the stream was done to me troubleshooting the problem. It turned out that I, for some reason, set while making the batches, like the 1 second, I'll show you guys. Oops. Yeah, for some reason, while making the data loader, I set shuffle to true, which should not have been a problem, but there was kind of a mismatch when we were trying to create the confusion matrix between the targets and the predictions. So anyhow, that was fixed, and yeah, let's move on. And okay, let's just continue with the course now. All right, so yesterday we kind of left out midway around the 19 to 20 hour mark. So
there are many new roles in tech, like DevOps, SRE, Cloud Engineer, and
in torch.load in here, and the file that we want to load, or the file path, if
we
my
did this, we also saved and
pretty closely.
Loaded?
Now I say
Is
pretty
that a
closely
word?
because
Is
you might
loaded
find
a
some
word?
discrepancy.
Oh no, that's a shop near me. Is loaded word. I guess it is.
Discrepancies in these lower decimals here, just because of the way files get saved and something gets lost, etc., etc. So that's just to do with precision in computing. But as long as like the first few numbers are quite similar, well, then we're all gravy. So let's go torch, manual seed. Remember, evaluating a model is almost as, well, it's just as important as training a model. So this is what we're doing. We're making sure our model's saved correctly. Before we deployed it, if we deployed it and it didn't save correctly, well, then we would get less than ideal results, wouldn't we? So model equals loaded model 2. We're going to use our same eval model function by putting our loss. It's similar to 829. Loaded model is too close. It's within quite large, but if goodness, look how much computer vision. So let's have a look at those in the next video. I'll see you there. My goodness. Look how much computer vision PyTorch code we've written together. We started off right up the top. We looked at the reference notebook and the online book. We checked out computer vision libraries in PyTorch, the main one being Torch Vision. Then we got a data set, namely the fashion MNIST data set. There are a bunch more data sets that we could have looked at. And in fact, I encourage you to try some out in the Torch Vision data sets. Use all of the steps that we've done here to try it on another data set. We prepared our data loaders, so turned our data into batches. We built a baseline model, which is an important step in machine learning because the baseline model is usually relatively simple, and it's going to serve as a baseline that you're going to try and improve upon through, just go back to the keynote, through various experiments. We then made predictions with Model 0. We evaluated it. We timed our predictions to see if running our models on the GPU was faster, and we learned that sometimes the GPU won't necessarily speed up code if it's a relatively small data set because of the overheads between copying data from CPU to GPU. We tried a model with nonlinearity, and we saw that it didn't really improve upon our baseline model. But then we brought in the big guns, a convolutional neural network, replicating the CNN Explainer website, and saw that it didn't really improve upon a relatively small data set because of the overheads between copying data from CPU to GPU. We tried a model with nonlinearity, and we saw that it didn't really improve upon our baseline model. But then we brought in the big guns, a convolutional neural network, replicating the CNN Explainer website, and my gosh, didn't we spend a lot of time here? I'd encourage you, as part of your extra curriculum, to go through this again and again. I still even come back to refer to it too. I refer to it a lot making the materials for this video section and this code section. So be sure to go back and check out the CNN Explainer website for more of what's going on behind the scenes of your CNNs. But we coded one using pure PyTorch. That is amazing. We compared our model results across different experiments. We found that our convolutional neural network did the best, although it took a little bit longer to train. And we also learned that the training time values will definitely vary depending on the hardware you're using. So that's just something to keep in mind. We made and evaluated random predictions with our best model, which is an important step in visualizing your model's predictions, because you could get evaluation metrics, but until you start to actually visualize what's going on, well, in my case, that's how I best understand what my model is thinking. We saw a confusion matrix using two different libraries, Torch Metrics and ML Extend, a great way to evaluate your classification models. And we saw how to save and load the best performing model to file and made sure that the results of our saved model weren't too different from the model that we trained within the notebook. So now it is time. I'd love for you to practice what you've gone through. This is actually really exciting now because you've gone through an end-to-end computer vision problem. I've got some exercises prepared. If you go to the learnpytorch.io website in section 03, scroll down, you can read through all of this. This is all the materials that we've just covered in pure code. There's a lot of pictures in this notebook too that are helpful to learn things what's going on. We have some exercises here. So all of the exercises are focused on practicing the code in the sections above. We have 2 resources. We also have some extra curriculum that I've put together. If you want an in-depth understanding of what's going on behind the scenes in the convolutional neural networks, because we focused a lot on code, I'd highly recommend MIT's Introduction to Deep Computer Vision lecture. You can spend 10 minutes flicking through the different options in the Pytorch Vision library, Torch Vision, look up most common convolutional neural networks in the Torch Vision model library, and then for a larger number of pre-trained Pytorch computer vision models, and if you get deeper into computer vision, you're probably going to run into the Torch image models library, otherwise known as TIM. But I'm going to leave that as extra curriculum. I'm going to just link this exercises section here. Again, it's at learnpytorch.io.
You know what?
Exercises section.
Check out TIM, the last link over there. TIM library. Is that it? Pytorch image models. I know Fast API, but I'm here looking at Fast AI for the first time. Fast AI simplifies training fast and accurate neural nets using modern best practices. What is ResNet 32? Okay, just an architecture for CNN. Alright, let's go back to the tutorial.
We come down. There we go. But there is also a resource here, an exercise template notebook. So we've got what are 3 areas in industry where computer vision has been currently used. Now this is in the Pytorch Deep Learning repo, extras, exercises number 3. I put out some template code here for you to fill in these different sections. So some of them are code related, some of them are just text-based, but they should all be able to be completed by referencing what we've gone through in this notebook here. And just as one more, if we go back to Pytorch Deep Learning, this will probably be updated by the time you get here. You can always find the exercise and extra curriculum by going computer vision, go to exercise and extra curriculum. Or if we go into the extras file and then we go to solutions, I've now also started to add video walkthroughs of each of the solutions. So this is me going through each of the exercises myself and coding them. And so you'll get to see the unedited videos, so they're just one long live stream. And I've done some for 02, 03, and 04, and there will be more here by the time you watch this video. But if you'd like to see how I figure out the solutions to the exercises, you can watch those videos and go through them yourself. But first and foremost, I would highly recommend trying out the exercises on your own first. And then if you get stuck, refer to the notebook here, refer to the Pytorch documentation, and finally, you can check out what I would have coded as a potential solution. So there's number 3, computer vision, exercise solutions. So congratulations on going through the Pytorch computer vision section. I'll see you in the next section. We're going to look at Pytorch custom datasets. But no spoilers. I'll see you soon. Hello, and welcome to...
the logo, or maybe the logo would still be a flamethrower. That effect was, that sound was good though. Let's play it again.
See you soon.
Let's play it again. Hello,
and welcome to section number 4 of the Learn Pytorch for Deep Learning course. We have...
Hello. Can you hear me? Hello. Never mind me, I'm just speaking to myself through the voice that I put, like, what I speak into the microphone comes back to me through the headphones. So I just want to check whether that was clear. Anyways, let's continue.
Custom datasets with Pytorch. Now, before we dive into what we're going to cover, let's answer the most important question. Where can you get help? Now, we've been through this a few times now, but it's important to reiterate. Follow along with the code as best you can. We're going to be writing a bunch of Pytorch code. Remember the motto, if in doubt, run the code. That's in line with try it for yourself. If you'd like to reach or read the doc string, you can press Shift Command plus Space in Google Colab, or if you're on Windows, Command might be Control. Then if you're still stuck, you can search for it. 2 of the resources you'll probably come across is Stack Overflow or the wonderful Pytorch documentation, which we've had a lot of experience with so far. Then of course, try again, go back through your code. If in doubt, code it out, or if in doubt, run the code. And then finally, if you're still stuck, ask a question on the Pytorch Deep Learning discussions GitHub page. So if I click this link, we come to Mr. Debug/Pytorch Deep Learning. The URL is here. We've seen this before. If you have a trouble or a problem with any of the course, you can start a discussion. And you can select the category, general, ideas, polls, Q&A, and then we can go here. Video, put the video number in, so 99 for example. My code doesn't do what I'd like it to. So say your problem, and then come in here, write some code here, and then my question is something. Click start discussion, and then we can help out. And then if we come back to discussions, of course, you can search for what's going on. So if you have an error and you feel like someone else might have seen this error, you can of course search it and find out what's happening. Now, I just want to highlight again, the resources for this course are at learnpytorch.io. We are up to section 4. This is a beautiful online book version of all the materials we are going to cover in this section. So spoiler alert, you can use this.
This is why I don't like yeah, I don't know if you saw that there was a mosquito around flying around here.
This is a reference. And then of course in the GitHub, we have the same notebook here, Pytorch custom datasets. This is the ground truth notebook. So check that out if you get stuck. So I'm just going to exit out of this. We've got Pytorch custom datasets at learnpytorch.io, and then of course the discussions tab for the Q&A. Now if we jump back to the keynote, what do we have? We might be asking, what is a custom dataset? Now we've got a fair few Pytorch deep learning neural networks so far on various datasets such as Fashion MNIST, but
for the timing, let's just expand the screen.
you might be wondering, hey, I've got my own dataset, or I'm working on my own problem. Can I build a model with Pytorch to predict on that dataset? And the answer is yes. However, you do have to go through a few pre-processing steps to make that dataset compatible with Pytorch. And that's what we're going to be covering in this section. And so I'd like to highlight the Pytorch domain libraries. Now we've had a little bit of experience before with Torch Vision, such as if we wanted to classify whether a photo was of pizza, steak, or sushi. So a computer vision image classification problem. Now there's also text, such as if these reviews are positive or negative. And you can use Torch text for that. But again, these are only just one problem within the vision space, within the text space. I want you to just understand that if you have any type of vision data, you probably want to look into Torch Vision. And if you have any kind of text data, you probably want to look into Torch Text. And then if you have...
What song is playing? Is that, what's it called? Shazam, right?
audio, such as if you wanted to classify what song was playing, this is what Shazam does. It uses the input sound of some sort of music and then runs a neural network over it to classify it to a certain song. You can look into Torch Audio for that. And then if you'd like to recommend something, such as you have an online store, or if you're Netflix or something like that, and you'd like to have a homepage that updates for recommendations, you'd like to look into Torch Rec, which stands for Recommendation System. And so this is just something to keep in mind. Because each of these domain libraries has a datasets module that helps you work with different datasets from different domains. And so different domain libraries contain data loading functions for different data sources. So Torch Vision, let's just go into the next slide. We have problem space, vision. For pre-built datasets, so existing datasets like we've seen with Fashion MNIST, as well as functions to load your own vision datasets, you want to look into torchvision.datasets. So if we click on this, we have built-in datasets. This is the Pytorch documentation. And if we go here, we have Torch Audio, Torch Text, Torch Datasets. So if we click on this, we have built-in datasets. This is the Pytorch documentation. And if we go here, we have Torch Audio, Torch Text, Torch Vision, Torch Rec, Torch Data. Now, at the time of recording, which is April 2022, Torch Data is currently in beta, but it's going to be updated over time. So just keep this in mind, updated over time to add even more ways to load different data resources. But for now, we're just going to get familiar with Torch Vision datasets. If we went into Torch Text, there's another Torch Text.datasets. And then if we went into Torch Audio, we have Torch Audio.datasets. And so you're noticing a trend here that depending on the domain you're working in, whether it be vision, text, audio, or your data is recommendation data, you probably want to look into its custom library within Pytorch. And of course, the bonus is Torch Data. It contains many different helper functions for loading data. And so you're noticing a trend here that depending on the domain you're working in, whether it be vision, text, audio, or your data is recommendation data, you probably want to look into its custom library within Pytorch. And of course, the bonus is Torch Data. It contains many different helper functions for loading data, and it's currently in beta as of April 2022. So by the time you watch this, Torch Data may be out of beta, and then that should be something that's extra curriculum on top of what we're going to cover in this section. So let's keep going. So this is what we're going to work towards building. Food Vision Mini. So we're going to load some data, namely some images of pizza, sushi, and steak from the Food 101 dataset. We're going to build an image classification model, such as the model that might power a food vision recognition app or a food image recognition app. And then we're going to see if it can classify an image of pizza as pizza, an image of sushi as sushi, and an image of steak as steak. So this is what we're going to focus on. We want to load, say we had images existing already of pizza, sushi, and steak. We want to write some code to load these images of food, so our own custom dataset for building this Food Vision Mini model, which is quite similar to if you go to, this is the project I'm working on personally, Nutrify.app. This is a food image recognition model. Here we go. So it's still a work in progress as I'm going through it. But you can upload an image of food, and Nutrify will try to classify what type of food it is.
I think, I don't know whether we had visited the site in one of the previous streams, but yeah, I think they have released now. There you go, Nutrify. I wonder how's it doing. Maybe I should download it later on.
It is. So do we have steak? There we go. Let's upload that. Beautiful. Steak. So we're going to be building a similar model to what powers Nutrify. So do we have steak? There we go. Let's upload that. Beautiful. Steak. So we're going to be building a similar model to what powers Nutrify. And then there's the macronutrients for the steak. Yada, yada, yada. If you'd like to find out how it works, I've got all the links here, but that's at Nutrify.app. So let's keep pushing forward. We'll go back to the keynote. This is what we're working towards. As I said, we want to load these images into Pytorch so that we can build a model. We've already built a computer vision model. So we want to figure out how do we get our own data into that computer vision model. And so, of course, we'll be adhering to our Pytorch workflow that we've used a few times now. So we're going to learn how to load a data set with our own custom data rather than an existing data set within Pytorch. We'll see how we can build a model to fit our own custom data set. We'll go through all the steps that's involved in training a model, such as picking a loss function and an optimizer. We'll build a training loop. We'll evaluate our model. We'll improve through experimentation. And then we can see save and reloading our model, but we're also going to practice predicting on our own custom data, which is a very, very important step whenever training your own models. So what we're going to cover broadly, we're going to get a custom data set with Pytorch, as we said. We're going to become one with the data. In other words, preparing and visualizing it. We'll learn how to transform data for use with a model, very important step. We'll see how we can load custom data with pre-built functions and our own custom functions. We'll build a computer vision model, aka Food Vision Mini, to classify pizza, steak, and sushi images, so a multi-class classification model. We'll compare models with and without data augmentation. We haven't covered that yet, but we will later on. And finally, we'll see how we can, as I said, make predictions on custom data. So this means data that's not within our training or our test data set. And how are we going to do it? Well, we could do it cooks or chemists, but I like to treat machine learning as a little bit of an art, so we're going to be cooking up lots of code. With that being said, I'll see you in Google Colab. Let's code. Welcome back to the Pytorch Cooking Show. Let's now learn how we can cook up some custom data sets. I'm going to jump into Google Colab, so colab.research.google.com. And I'm going to
create a new notebook.
new notebook. Just going to make sure this is zoomed in enough for the video. Wonderful. So I'm going to rename this notebook 04, because we're up to section 04. And I'm going to call it Pytorch Custom Datasets _ video, because this is going to be one of the video notebooks, which has all the code that I write during the videos, which is of course contained within the video notebooks folder on the Pytorch Deep Learning repo. So if you'd like the resource or the ground truth notebook for this, I'm going to just put a heading here, 04 Pytorch Custom Datasets video notebook. Make that bigger. And then we'll put resources. So book version of the course materials for 04. We'll go there, and then we'll go ground truth version of notebook 04, which will be the reference notebook that we're going to use for this section. Come into Pytorch Custom Datasets, and then we can put that in there. Wonderful. So the whole synopsis of this custom dataset section is we've used some datasets with Pytorch before, but how do you get your own data into Pytorch? Because that's what you want to start working on, right? You want to start working on problems of your own. You want to come into any sort of data that you've never worked with before, and you want to figure out how do you get that into Pytorch. So one of the ways to do so is via custom datasets. And then I want to put a note down here. So we're going to go 0, section 0 is going to be importing Pytorch and setting up device agnostic code. But I want to just stress here that domain library.
Before we begin with this, I think it's a good time to just look to the unofficial Pytorch song. Yep, there we go.
Oh, excuse me. If I'd known Pyloop and a Pytorch bus, I never forget. So let's train. For an epoch in a range, Komodo.train, do the forward pass, calculate the loss, optimize a zero grad, loss backwards, optimize a step, step, step. Let's test. Komodo.eval with torch inference mode, do the forward pass, calculate the loss, print out what's happening. Let's do it again, again, again. For another epoch, Komodo.train, do the forward pass, calculate the loss, optimize a zero grad, loss backwards, optimize a step, step, step. Let's test. Komodo.eval with torch inference mode, do the forward pass, calculate the loss, print out what's happening.
I think that song I'll never forget how to. As Daniel rightfully mentioned, because I'll never forget how to write the optimization loop. Well, I guess in practice, everyone just uses functions, but it's a pretty good done song.
So, just to reiterate what we went through last video, so depending on what you're working on, whether it be vision, text, audio, recommendation, something like that, you'll want to look into each of the Pytorch domain libraries for existing data loader or data loading functions and customizable data loading functions. So just keep that in mind. We've seen some of them. So if we go Torch Vision, which is what we're going to be looking at, Torch Vision, we've got datasets and we've got documentation, we've got datasets for each of the other domain libraries here as well. So if you're working on a text problem, it's going to be a similar set of steps to what we're going to do with our vision problem when we build Food Vision Mini. What we have is a dataset that exists somewhere, and what we want to do is bring that into Pytorch so we can build a model with it. So let's import the libraries that we need. So we're going to import Torch, and we'll probably import NN. So we'll import that to Pytorch. And I'm just going to check the Torch version here. So note, we need Pytorch 1.10.0 plus is required for this course. So if you're using Google Colab at a later date, you may have a later version of Pytorch. I'm just going to show you what version I'm using. Just going to let this load. we're going to get this ready. We're going to also set up device agnostic code right from the start this time, because this is best practice with Pytorch. So this way, if we have a CUDA device available, our model is going to use that CUDA device, and our data is going to be on that CUDA device. So there we go, wonderful. We've got Pytorch 1.10.0 plus CUDA 1.1.1, maybe that's 11.1. So let's check if CUDA dot is available. Now, I'm using Google Colab. We haven't set up a GPU yet, so it probably won't be available yet. Let's have a look. Wonderful. So because we've started a new Colab instance, it's going to use the CPU by default. So how do we change that? We come up to runtime, change runtime type. I'm going to go hardware accelerator, GPU. We've done this a few times now. I am paying for Google Colab Pro. So one of the benefits of that is that Google Colab reserves faster GPUs for you. You do not need Google Colab Pro, as I've said, to complete this course. You can use the free version, but just recall Google Colab Pro tends to give you a better GPU just because GPUs aren't free. Wonderful. So now we've got access to a GPU. CUDA, what GPU do I have? NVIDIA SMI. I have a Tesla P100 with 16 gigabytes of memory, which will be more than enough for the problem that we're going to work on in this video. So I believe that's enough to cover for the first coding video. Let's in the next section. We are working with custom datasets after all. Let's in the next video. Let's get some data, hey? Now, as I said in the last video, we can't cover custom datasets without some data. So let's get some data and just remind ourselves what we're going to build, and that is Food Vision Mini. So we need a way of getting some food images. And if we go back to Google Chrome, Torch Vision datasets has plenty of built-in datasets, and one of them is the Food 101 dataset. Food 101. So if we go in here, this is going to take us to the original Food 101 website. So Food 101 is 101 different classes of food. It has a challenging dataset of 101 different food categories with 101,000 images. So that's quite a beefy dataset. And so for each class, 250 manually reviewed test images are provided. So we have per class, 101 classes, 250 testing images, and we have 750 training images. Now, we could start working on 1,000 images. So that's quite a beefy dataset. And so for each class, 250 manually reviewed test images are provided. So,
oh, I see. So for each class, so for let's say steak, 250 steak images are provided for as test images and 750 for training.
we have per class, 101 classes, 250 testing images, and we have 750 training images. Now, we could start working on this entire dataset straight from the get-go, but to practice, I've created a smaller subset of this dataset, and I'd encourage you to do the same with your own problems. Start small and upgrade when necessary. So I've reduced the number of categories to 3, and the number of images to 10%. Now, you could reduce this to an arbitrary amount, but I just decided 3 is enough to begin with, and 10% of the data. And then if it works, hey, you could upscale that on your own accord. And so I just want to show you the notebook that I used to create this dataset, and as extra curriculum, you could go through this notebook. So if we go into extras, 04 custom data creation, this is just how I created the subset of data. So making a dataset to use with notebook number 4, I created it in custom image dataset or image classification style. So we have a top level folder of pizza, steak, and sushi. We have a training directory with pizza, steak, and sushi images, and we have a test directory with pizza, steak, and sushi images as well. So you can go through that to check it out how it was made. But now, oh, and also, if you go to learnpytorch.io section 4, there's more information here about what Food 101 is. So get data. Here we go. There's all the information about Food 101. There's some resources, the original Food 101 dataset, Torch Vision datasets, Food 101, how I created this dataset, and actually downloading the data. But now we're going to write some code because this dataset, the smaller version that I've created, is on the Pytorch deep learning repo under data. And then we have pizza steak sushi.zip. Oh, this one is a little spoiler for one of the exercises for this section, but you'll see that later. So let's go in here. Let's now write some code to get this dataset from GitHub, pizza steak sushi.zip, and then we'll explore it. We'll become one with the data. So I just want to write down here. Our dataset is a subset of the Food 101 dataset. Food 101 starts with 101 different classes of food. So we could definitely build computer vision models for 101 classes, but we're going to start smaller. Our dataset starts with 3 classes of food and only 10% of the images. So let's write here, and 1,000 images per class, which is 750 training, 250 testing, and we have about 75 training images per class and about 25 testing images per class. So why do this? When starting out ML projects, it's important to try things on a small scale and then increase the scale when necessary. The whole point is to speed up how fast you can experiment. Because there's no point trying to experiment on things that if we try to train on 100,000 images to begin with, our models might take half an hour to train at a time. So at the beginning, we want to increase the rate that we experiment at. And so let's get some data. We're going to import requests so that we can request something from GitHub to download this URL here. Then we're also going to import zip file from Python because our data is in the form of a zip file right now. Then we're going to get pathlib because I like to use paths whenever I'm dealing with file paths or directory paths. So now let's set up a path to a data folder. And this, of course, will depend on where your dataset lives, what you'd like to do, but I typically like to create a folder over here called data. And that's just going to store all of my data for whatever project I'm working on. So data path equals path data. And then we're going to go image path equals data path / pizza, steak, sushi. That's we're going to have images from those 3 classes. Pizza, steak, and sushi are 3 of the classes out of the 101 in Food 101. So if the image folder doesn't exist, so if our data folder already exists, we don't want to re-download it. But if it doesn't exist, we want to download it and unzip it. So if image path is dir, so we want to print out the image path directory already exists, skipping download. And then if it doesn't exist, we want to print image path does not exist, creating one. Beautiful. And so we're going to go imagepath.mkdir to make a directory. We want to make its parents if we need to the parent directories, and we want to pass exist OK equals true so we don't get any errors if it already exists. And so then we can write some code. I just want to show you what this does if we run it. So our target directory data / pizza steak sushi does not exist. It's creating one. So then we have now data, and inside pizza steak sushi. Wonderful. But we're going to fill this up with some images so that we have some data to work with. And
But I made the directory directory. Yeah.
It's creating one. So then we have now data, and inside pizza, steak, sushi. Wonderful. But we're going to fill this up with some images so that we have some data to work with. And then the whole premise of this entire section will be loading this data of just images into Pytorch so that we can build a computer vision model on it. But I just want to stress that this step will be very similar no matter what data you're working with. You'll have some folder over here, or maybe it'll live on the cloud somewhere. Who knows wherever your data is, but you'll want to write code to load it from here into Pytorch. So let's.
But for some reason, it did not create. No, never mind. It created the pizza, sushi, steak folder. Or rather, pizza, steak, sushi folder.
Let's download pizza, steak, and sushi data. So I'm going to use with. I'll just X over here so we have more screen space. With open, I'm going to open the data path / the file name that I'm trying to open, which will be pizzasteaksushi.zip, and I'm going to write binary as F. So this is essentially saying I'm doing this in advance because I know I'm going to download this folder here. So I know the file name of it, pizzasteaksushi.zip. I'm going to download that into Google Colab, and I want to open it up. So request equals request.get. And so when I want to get this file, I can click here. And then if I click download, it's going to, what do you think it's going to do? Well, let's see. If I wanted to download it locally, I could do that. And then I could come over here.
You can just do image. Oh no, because it has a .zip attached to it. The extension is attached.
And then I could click upload if I wanted to. So upload the session storage, I can upload it from that. But I prefer to write code so that I could just run this cell over again and have the file, instead of being downloaded to my local computer, it just goes straight into Google Colab. So to do that, we need the URL from here.
Right, and let's copy that URL from GitHub. So we are going to need. Now I need the raw version. So how do I get that? Oh no, that downloaded the. I didn't want to download it. Is it? What did we do for this to work the last time? Okay, let's just see what.
And I'm just going to put that in there.
Copying.
It needs to be as a string.
Oh, he just copied this link. Okay, we'll do the same then.
Excuse me. I'm getting trigger happy on the shift and enter. Wonderful. So now I've got a request to get the content that's in here. And GitHub can't really show this because this is a zip file of images. Spoiler alert. Now let's keep going. We're going to print out that we're downloading pizza, steak, and sushi data. ... And then I'm going to write to file the request.content. So the content of the request that I just made to GitHub. So that's request is here, using the Python request library to get the information here from GitHub. This URL could be wherever your file is being stored. And then I'm going to write the content of that request to my target file, which is this here. So if I just copy this, I'm going to write the data to here, data path / pizza steak sushi zip. And then because it's a zip file, I want to unzip it. So unzip pizza steak sushi data. Let's go with zip file. So we imported zip file up there, which is a Python library to help us deal with zip files. I'm going to use zip file. I'm going to pass it in the data path. So just the path that we did below, data path / pizza steak sushi.
It's my first time using this.
And this time instead of
file
giving it
module.
write permissions, so that's what WB stands for. It stands for write binary. I'm going to give it read permissions, so I want to read this target file instead of writing it. And I'm going to go as zipref. We can call this anything really, but zipref is kind of, you'll see this a lot in different.
Okay, you know what? We're just gonna make zip file name. Yep, we're gonna call it that. And just paste that in instead.
Different Python examples. So we're going to print out again. So unzipping pizza, steak, and
What does REF stand for though?
want to read.
I
this
mean,
target
I
file
know
instead
it's
of
a
writing it.
variable name, but like, what's the idea behind that convention?
And I'm going to go as zipref. We can call this anything really, but zipref is kind of, you'll see this a lot in different Python examples. So we're going to print out again.
So yet again another one of those things where you don't question why it is, you just follow.
So
Right.
unzipping pizza, steak, and sushi data. Then we're going to go zip underscore ref dot extract all, and we're going to go image path. So what this means is it's taking the zip ref here, and it's extracting all of the information that's within that zip ref, so within this zip file, to the image path, which is what we created up here. So if we have a look at image path, let's see that. Image path. Wonderful. So that's where all of the contents of that zip file are.
Before this, I haven't actually used. I knew that the pathlib module existed, but I didn't use it for almost anything related to path, path related stuff. I just stuck to normal Python code for that. But I think I need to step up my game and use it more frequently because it's such a handy module, isn't it?
Are going to go into this file. So let's see it in action. You ready? Hopefully it works. 3, 2, 1, run. File is not a zip file. Oh no, what did we get wrong? So did I type this wrong? Got zip, data path. Oh, we got the zip file here. Pizza steak sushi, not zip, read, data path. Okay, I found the error. So this is another thing that you'll have to keep in mind, and I believe we've covered this before, but I like to keep the errors in these videos so that you can see where I get things wrong, because you never write code right the first time. So we have this.
Yeah, it's the URL
link in GitHub. We have to make sure that we have the raw link address. So if I come down to here and copy the link address from the download button, you'll notice a slight difference if we come back into here. So I'm just going to copy that there.
All right, so let's do that. I need the link. How come Dino has a download button whereas I don't? Just have this. Oh, maybe this is where I need to commit to. But how do I? No, I don't wanna download. I want the URL for this. Okay, we're gonna do a thing here. Why is I didn't change it, did I, from my HTML session yesterday? Anyhow, download. Okay, now I can get the URL, can't I? That's fun way of doing it, I guess. Yep, that should do it, hopefully.
Come down to here and copy the link address from the download button. You'll notice a slight difference if we come back into here. So I'm just going to copy that there. So if we step through this, GitHub, Mr. Debug, Pytorch Deep Learning, we have raw instead of blob. So that is why we've had an error, is that our code is correct. It's just downloading the wrong data. So let's change this to the raw. So just keep that in mind. You must have raw here. And so let's see if this works. Do we have the correct data? Oh, we might have to delete this. Oh, there we go. Test. Beautiful. Train. Pizza, steak, sushi. Wonderful. So it looks like we've got some data. And if we open this up, what do we have? We have various JPEGs. Okay, so this is our testing data. And if we click on there, we've got an image of pizza. Beautiful. So we're going to explore this a little bit more in the next video, but that is some...
That pizza looks good. Why is it burned on the side though? It's burned on the side a bit. I guess that's how a pizza should be. A traditional pizza should be. Yeah, anyway. So let's take a look. Gosh, I'm gonna get hungry after this. That's a zoomed in picture. That's just a pizza slice. Okay, I'm gonna get hungry by looking at these. So now what does steak look like? Other than pizza, I haven't had steak, neither steak nor sushi. Should try them out. But sushi? Hey, that looks like sushi to me. Okay, I'm getting hungry. Okay, let me just close the images and yeah. Anyway, we have the data set now, so
the code that we've written to download datasets or download our own custom dataset. Now, just recall that we are working specifically on a pizza, steak, and sushi problem for computer vision. However, our whole premise is that we have some custom data and we want to convert these. How do we get these into tensors? That's what we want to do. And so the same process will be for your own problems. We'll be loading a target dataset and then writing code to convert whatever the format the dataset is in into tensors for Pytorch. So I'll see you in the next video. Let's explore the data we've downloaded. Welcome back. In the last video, we wrote some code to download a target dataset, our own custom dataset from the Pytorch Deep Learning data directory. And if you'd like to see how that dataset was made, you can go to Pytorch Deep Learning /extras. It's going to be in the custom data creation notebook here for 04. So I've got all the code there. All we've done is take data from the Food 101 dataset, which you can download from this website here, or from Torch Vision. So if we go to Torch Vision Food 101, we've got the dataset built into Pytorch there. So I've used that dataset from Pytorch and broken it down from 101 classes to 3 classes so that we can start with a small experiment. So
I mean, Torch Vision doesn't have the, like, it doesn't come with the module, right? It helps us to download. Oh yeah, there we go. I was looking at the docs and just, yeah.
It says Food 101, and then I've customized it to be my own style. So if we go back to Colab, we've now got pizza steak sushi, a test folder which will be our testing images, and a train folder which will be our training images. This data is in standard image classification format. We'll cover that in a second. What we're going to do in this video is kick off section number 2, which is becoming one with the data, which is one of my favorite ways to refer to data
Becoming
preparation.
one with the data.
And data
I like how he wanted that out.
exploration. So becoming one with the data. And
I also like how he pronounced that out.
just like to show you one of my favorite quotes from Abraham Loss Function. So if I had 8 hours to build a machine learning model, I'd spend the first 6 hours preparing my dataset.
All right. I guess that says a lot about how important dataset preparation is.
And that's what we're going to do. Abraham Loss Function sounds like he knows what is going on, but since we've just downloaded some data, let's explore it, hey? And we'll write some code now to walk through each of the directories. How you explore your data will depend on what data you've got. So we've got a fair few different directories here with a fair few different folders within them. So how about we walk through each of these directories and see what's going on? If you have visual data, you probably want to visualize an image. So we're going to do that in a second too. Write a little doc string for this helper function. So walks through dir path, returning its contents. Now, just in case you didn't know, Abraham Loss Function does not exist as far as I know, but I did make up that quote. So we're going to use the os.walk function, os.walk, and we're going to pass it in a dir path. And what does walk do? We can get the doc string here. Directory tree generator. For each directory in the directory tree, rooted at the top, including top itself, but excluding dot and dot dot, yields a 3-tuple: dir path, dir names, and file names. You can step through this in the Python documentation if you'd like, but essentially it's just going to go through our target directory, which in this case will be this one here.
I think I lost my train of thought.
And walk through each of these directories, printing out some information about each one. So let's see that in action. This is one of my favorite things to do if we're working with standard image classification format data. So there are length dir names, directories, and let's go len, file names. I say length like I've got the G on the end, but it's just len. Images in, let's put in here, dir path. So a little bit confusing if you've never used walk before, but it's so exciting to see all of the information in all of your directories. Oh, we didn't run it. Let's check out function now. Walk through dir, and we're going to pass it in the image path, which is what? Well, it's going to show us. Oh, beautiful. So let's compare what we've got in our print. Print out here, and we're going to pass it in the image path, which is what? Well, it's going to show us. Oh, beautiful. So let's compare what we've got in our printout here. There are 2 directories and 0 images in data pizza steak sushi. So this one here, there's 0 images, but there's 2 directories.
Let's see, missing. Of course, I need to provide it with the image path now, don't I? Let's do that, and nope, made it right to there. That should be good. There are 2 directories and 0 images in, of course, yeah. This is the train and test directory. Okay, I think yeah. So we have 72 sushi images, training sushi images, I should say, and 31 what's it, testing. Shouldn't this be like kind of equal though? Why is it
Directories. Test and train, wonderful.
alternate?
And there are 3 directories in data pizza steak sushi test.
I think
Yes, that's correct,
he
3
wants us to prepare the data, maybe. Of course, the heading says so. Anyway,
Pizza steak sushi. And then we have 0 directories and 19 images in pizza steak sushi /test steak. We have a look at this. So that means there's 19 testing images for steak. Let's have a look at one of them. There we go. Now, again, these are from the Food 101 dataset, the original Food 101 dataset, which is just a whole bunch of images of food, 100,000 of them. There's some steak there. Wonderful. And we're trying to build a food vision model to recognize what is in each image. Then if we jump down to here, we have 3 directories in the training directory. So we have pizza steak sushi, and then we have 75 steak images, 72 sushi images, and 78 pizza. So slightly different, but very much the same numbers. They're not too far off each other. So we've got about 75 or so training images, and we've got about 25 or so testing images per class. Now these were just randomly selected from the Food 101 dataset, 10% of 3 different classes. So let's keep pushing forward, and we're going to set up our training and test paths. So I just want to show you, we'll just set up this, and then I'll just show you the standard image classification setup. Image path.train, and we're going to go tester. So if you're working on an image classification problem, we want to set this up as test. And then if we print out the trainer and the tester, this is what we're going to be trying to do. We're going to write some code to go, hey, look at this path for our training images, and look at this path for our testing images. And so this is the standard image classification data format, is that you have your overall dataset folder, and then you have a training folder dedicated to all of the training images that you might have, and then you have a testing folder dedicated to all of the testing images that you might have. And you can have a validation dataset here as well if you wanted to. But to label each one of these images, the class name is the folder name. So all of the pizza images live in the pizza directory. The same for steak, and the same for sushi. So depending on your problem, your own data format will depend on whatever you're working on. You might have folders of different text files or folders of different audio files. But the premise remains, we're going to be writing code to get our data here into tensors for use with Pytorch. And so where does this come from, this image data classification format? Well, if we go to the torchvision.datasets documentation, as you start to work with more datasets, you'll start to realize that there are standardized ways of storing specific types of data. So if we come down to here, base classes for custom datasets, we'll be working towards using this image folder dataset. But this is a generic data loader where the images are arranged in this way by default. So I've specifically formatted our data to mimic the style that this pre-built data loading function is for. So we've got a root directory here in case of...
so it can do a bunch of stuff for us, right?
Specifying dog and cat images. We have root, then we have a dog folder, then we have various images. And the same thing for cat. This would be dog versus cat. But the only difference for us is that we have food images and we have pizza steak sushi. If we wanted to use the entire Food 101 dataset, we would have 101 different folders of images here, which is totally possible, but to begin with, we're keeping things small. So let's keep pushing forward. As I said, we're dealing with a computer vision problem. So what's another way to explore our data other than just walking through the directories themselves? Let's visualize an image, hey? But we've done that before with just clicking on the file. How about we write some code to do so? We'll replicate this, but with code. I'll see you in the next video. Welcome back. In the last video, we started to become one with the data, and we learned that we have about 75 images per training class and about 25 images per testing class. And we also learned that the standard image classification data structure is to have the steak images within the steak folder of the training dataset, and the same for test, and the pizza images within the pizza folder, and so on for each different image classification class that we might have. So if you want to create your own dataset, you might format it in such a way that your training images are living in a directory with their classification name. So if you wanted to classify photos of dogs and cats, you might create a training folder of train/dog, train/cat, put images of dogs in the dog folder, images of cats in the cat folder, and the same for the testing dataset. But the premise remains, I'm going to sound like a broken record here. We want to get our data from these files, whatever files they may be in, whatever data structure they might be in, into tensors. But before we do that, let's keep becoming one with the data, and we're going to visualize an image. So visualizing an image, and you know how much I love randomness. So let's select a random image from all of the files that we have in here, and let's plot it, hey? Because we could just click through them and visualize them, but I like to do things with code. So specifically, let's plan this out. Let's write some code to, number one, is get all of the image paths. We'll see how we can do that with the path lib library. We then want to pick a random image path using, we can use Python's random for that. Python's random.choice, we'll pick a single image, random.choice. Then we want to get the image class name. And this is where pathlib comes in handy. Class name, recall that whichever target image we pick, the class name will be whichever directory that it's in. So in the case of if we picked a random image from this directory, the class name would be pizza. So we can do that using, I think it's going to be pathlib.path, and then we'll get the parent folder, wherever that image lives, so the parent image, parent folder, that parent directory of our target random image, and we're going to get the stem of that. So we have stem. Stem is the last little bit here. Number 4, what should we do? Well, we want to open the image. So since we're working with images, let's open the image with Python's pill, which is Python image library, but will actually be pillow. So if we go Python pillow, a little bit confusing when I started to learn about Python image manipulation. So pillow is a friendly pill fork, but it's still called pill. So just think of pillow as a way to process images with Python. So pill is the Python imaging library by Frederick Lund. And so Alex Clark and contributors have created pillow. So thank you, everyone. And let's go to number 5. What do we want to do as well? We want to, let's get some metadata about the image. We'll then show the image and print metadata. Wonderful. So let's import random, because machine learning is all about harnessing the power of randomness, and I like to use randomness to explore data as well as model it. So let's set the seed. So we get the same image on both of our ends. So random.seed. I'm going to use 42. You can use whatever you'd like, but if you'd like to get the same image as me, I'd suggest using 42 as well. Now let's get all the image paths. So we can do this because our image path list, we want to get our image path. So recall that our image path is this. So this folder here. I'm just going to close all this. So this is our image path, this folder here. You can also go copy path if you wanted to. We're just going to get something very similar there. That's going to error out, so I'll just comment that. So it doesn't error. That's our path, but I'm going to keep it in the POSIX path format. And we can go list. Let's create a list of imagepath.glob, which stands for grab. I don't actually know what glob stands for, but to me, it's like glob together all of the images that, or all of the files that suit a certain pattern. So glob together for me means stick them all together. And you might be able to correct me if I've got the wrong meaning there. I'd appreciate that. And so we're going to pass in a certain combination. So we want star/star, and then we want star.jpg. Now, why are we doing this? Well, because we want every image path. So star is going to be this first directory here. So any combination, it can be train or test. And then this star means anything for what's inside test. So let's say this first star is equal to test. This second star is equal to anything here. So it could be any of pizza, steak, or sushi. And then finally this star, let's say it was test, pizza. This star is anything in here and that is before .jpg. So it could be any one of these files here. Now this will make more sense once we print it out. So image path list. Let's have a look. There we go. So now we've got a list of every single image that's within pizza, steak, sushi. And this is just another way that I like to visualize data, is to just get all of the paths and then randomly visualize it, whether it be an image or text or audio. You might want to randomly listen to it. Recall that each of the domain libraries have different input and output methods for different data sets. So if we come to Torch Vision, we have utils. So we have different ways to draw on images, reading and writing images and videos. So we could load an image via read image, we could decode it, we could do a whole bunch of things. I'll let you explore that as extra curriculum. But now let's select a random image from here and plot it. So we'll go number 2, which was our step up here. Pick a random image. So pick a random image path. Let's get rid of this. And so we can go random image path equals random.choice. Harness the power of randomness to explore our data. Let's get a random image from image path list, and then we'll print out random image path. Which one was our lucky image that we selected? Beautiful. So we have a test pizza image as our lucky random image. And because we've got a random seed, it's going to be the same one each time. Yes, it is. And if we comment out the random seed, we'll get a different one each time. We've got a steak image. We've got another steak image. Another steak image. Oh, 3 in a row. 4 in a row. Pizza. Okay, let's keep going. So we'll get the image class from the path name. So the image class.
In a row, what? Oh, okay. I thought he was getting the same pizza image 4 times in a row, which is mathematically, I don't know. It should be a very, what do you call a very really small number using a mathematical jargon? I think it's infinitesimal. I think that's anyway. You get what I mean, so I'll pause at that.
If we comment out the random seed, we'll get a different one each time. We've got a steak image. We've got another steak image. Another steak image. Oh, 3 in a row. 4 in a row. Pizza. Okay, let's keep going. So we'll get the image class from the path name. So the image class is the name of the directory, because our image data is in standard image classification format, where the image is stored. So let's do that. Image class equals random image path dot parent dot stem, and then we're going to print image class. What do we get? So we've got pizza. Wonderful. So the parent. Is this folder here, and then the stem is the end of that folder, which is pizza.
Okay.
Beautiful. Now, what are we up to now? We're working with images. Let's open up the image. So we can open up the image using pill. We can also open up the image with Pytorch here, so with read image, but we're going to use pill to keep things a little bit generic for now. So open image, image equals image. So from pill import image, and image class has an open function, and we're just going to pass it in here, the random image path. Note, if this is corrupt, if your image is corrupt, this may error. So then you could potentially use this to clean up your data set. I've imported a lot of images with image.open of our target data set here. Image, and image class has an open function, and we're just going to pass it in here, the random image path. Note, if this is corrupt, if your image is corrupt, this may error. So then you could potentially use this to clean up your data set. I've imported a lot of images with image.open of our target data set here. I don't believe any of them are corrupt, but if they are, please let me know. And we'll find out later on when our model tries to train on it. So let's print some metadata. So when we open our image, we get some information from it. So let's go, our random image path is what? Random image path. We're already printing this out, but we'll do it again anyway. And then we're going to go, the image class is equal to what? Will be the image class. Wonderful. And then we can print out, we can get some metadata about our images. So the image height is going to be img.height. We get that metadata from using the pill library. And then we're going to print out image width, and we'll get img.width, and then we'll print the image itself.
Right. And then we'll also print the width.
Wonderful. We can get rid of this. We can get rid of this.
What did I do that? Somehow did I skip through the video? Oh no, never mind.
Wonderful. We can get rid of this. We can get rid of this. Let's now have a look at some random images from our dataset. Lovely. We've got an image of pizza there. Now, I will warn you that
I thought our randomness was supposed to be the same. What's happening here?
The downsides of working with food data is it does make you a little bit... Lovely, we've got an image.
Not sure, maybe it's something to do with like it not being exactly the same, maybe. I'm not sure. Yeah.
Pizza there. Now, I will warn you that one of the downsides of working with food data is it does make you a little
Maybe our data set is different or something like that.
bit hungry. So there we've got some sushi, and then we've got some more sushi, some steak, and we have steak. We'll go one more for good luck, and we finish off with some sushi. Oh, that could be a little bit confusing to me. I thought that might be steak to begin with. And this is, do you see now?
Am I just gonna get the same image then? I think he turned off random seed. Okay, that might be it then. How do people make this kind of pattern though? That's some kind of dipping sauce, right? You use with sushi. I wouldn't know. I haven't eaten sushi. I haven't tried though. What kind of pizza is that? Like what are those crumbs on top of pizza? Of the pizza. I haven't seen such a pizza in my life. Okay, just plain cheese pizza. Not to self, don't do this when you're hungry. Don't train a food model when you're hungry. We'll stop when we get steak. Is that steak? Yeah, I think that's steak. One more steak image. Not sushi. No. 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 That was 4 pizzas, right? Oh, that were 4 pizzas. Um, pizza again. Sushi again. Okay, why aren't we getting any images of? There we go. That's a beautiful steak.
We'll do one more.
Alright.
Why it's important to sort of visualize your images randomly, because you never know what you're going to come across. And this way, once we visualize enough images, you could do this 100 more times, you could do this 20 more times, until you feel comfortable to go, hey, I feel like I know enough about the data now. Let's see how well our model goes on this sort of data. So we'll finish off on this steak image. And now I'll set you a little challenge before the next video, is to visualize an image like we've done here, but this time do it with matplotlib. So try to visualize an image with matplotlib. That's your little challenge before the next video. So give that a go. We want to do a random image as well. So quite a similar setup to this, but instead of printing out things like this, we want to visualize it using matplotlib.
How do you mean just display an image on matplotlib? Display image on matplotlib. Okay, we'll copy that and same thing. I mean, not exactly the same. But we're just gonna copy this random image path and yeah, we're gonna show that image. Hey, there we go. Maybe we'll remove the axis. Let's also set the title as the image class. And yeah, we don't need to print this or this. Okay, pizza. Steak. Pizza again.
So try that out and we'll do it together in the next video. Oh, we are well on the way to creating our own Pytorch custom dataset. We've started to become one with the data. But now let's continue to visualize another image. I set you the challenge in the last video to try and replicate what we've done here with the pill library with matplotlib. So now let's give it a go, hey? And why use matplotlib? Well, because matplotlib, and I'm going to import numpy as well because we're going to have to convert this image into an array. That was a little trick.
Convert the image into an array? Okay. I don't know, that was the challenge. Hey, anyway, let's just follow with the tutorial now.
That I didn't quite elaborate on, but I hope you tried to code it out and figure it out from the errors you received. But matplotlib is one of the most fundamental data science libraries, so you're going to see it everywhere. So it's just important to be aware of how to plot images and data with matplotlib. So turn the image into an array. So we can go image as array, and I'm going to use the numpy method, np as array. I'm going to pass it in an image. Recall that the image is the same image that we've just set up here, and we've already opened it with pill. And then I'm going to plot the image. So plot the image with matplotlib, plt.figure, and then we can go fig size equals 10, 7, and then we're going to go plt.imshow, image as array, pass it in the array of numbers. I'm going to set the title here as an f string, and then I'm going to pass in image class equals image class. Then I'm going to pass in image shape. So we can get the shape here. Now this is another important thing to be aware of your different data sets when you're exploring them, is what is the shape of your data? Because what's one of the main errors in machine learning and deep learning? It's shape mismatch issues. So if we know the shape of our data, we can start to go, okay, I kind of understand what shape I need my model layers to be in, what shape I need my other data to be in. I'm going to turn the axes off here. Beautiful. So look at what we've got. Now,
oh, hold on a second. I guess that's what this method does. ImRead does shorthand. Anyhow. But what's it? Pytorch needs it as color channels first, right? Pytorch requires color channels first. That should bring up the channel ordering. Channels first by default. Okay.
I've just thrown this in here without really explaining it, but we've seen this before in the computer vision section. Is our image shape is 512, 306, 3. Now the dimensions here are height is 512 pixels, the width is 300.
Why do we have this tuple?
6 pixels. Shape is 512, 306.
Not sure why we have the tuple over there, but we'll roll with it, I guess. And what else? What else?
Now the dimensions here are height is 512 pixels, the width is 306 pixels, and it has 3 color channels. So what format is this? This is color channels last, which is the default for the pill library. There's also the default for matplotlib, but Pytorch, recall, is default if we put the color channels at the start, color channels first. Now, there's a lot of debate, as I've said, over which is the best order. It looks like it's leading towards going towards this, but for now, Pytorch defaults to color channels first. But that's okay, because we can manipulate these dimensions to what we need for whatever code that we're writing. And the 3 color channels is what? Red, green, and blue. So if you combine red, green, and blue in some way, shape, or form, you get the different colors here that represent our image. And so if we have a look at our image as array, our image is in numerical format. Wonderful. So, okay, we've got one way to do this for one image. I think we start moving towards scaling this up to do it for every image in our data folder. So let's just finish off this video by visualizing one more image. What do we get? Same premise, the image is now...
Wait a second. Why? Oh, okay. Huh. So it shows us both the image and the image as an array. That's cool.
As an array, different numerical values. We've got a delicious looking pizza here of shape 512, 512 with color channels last. And we've got the same thing up here. So that is
Maybe
one
it's
way
an
to
inbuilt Functionality just for Google Colab, perhaps.
become one with the data is to visualize different images, especially random images. You could do the same thing, visualizing different text samples that you're working with or listening to different audio samples. It depends what domain you're working in. So now in the next video, let's start working towards turning all of the images in here. Now that we've visualized some of them and become one with the data, we've seen that the shapes are varying in terms of height and width, but they all look like they have 3 color channels because we have color images. But now we want to write code to turn all of these images into Pytorch tensors. So let's start moving towards that. I'll see you in the next video. Hello. And welcome back. In the last video, we converted an image to a NumPy array, and we saw how an image can be represented as an array. But what if we'd like to get this image from our custom dataset over here, pizza steak sushi, into Pytorch? Well, let's cover that in this video. So I'm going to create a new heading here, and it's going to be transforming data. And so what we'd like to do here is, I've been hinting at the fact the whole time, is we want to get our data into tensor format, because that is the data type that Pytorch accepts. So let's write down here, before we can use our image data with Pytorch, now this goes for images, other vision data, it goes for text, it goes for audio, basically whatever kind of data set you're working with, you need some way to turn it into tensors. So that's step number 1, turn your target data into tensors. In our case, it's going to be a numerical representation of our images. And number 2 is turn it into a torch.utils.data.dataset. So recall from a previous video that we've used the dataset to house all of our data in tensor format. And then subsequently, we turned our datasets, our Pytorch datasets, into torch.utils.data.dataLoader. And a data loader creates an iterable or a batched version of our dataset. So for short, we're going to call these dataset and data loader. Now, as I discussed previously, if we go to the Pytorch documentation, Torch Vision, for Torch Vision, this is going to be quite similar for Torch Audio, Torch Text, Torch Rec, Torch Data eventually when it comes out of beta. There are different ways to create such datasets. So we can go into the datasets module, and then we can find built-in datasets, and then also base classes for custom datasets. But if we go into here,
I will use the GPU runtime. Okay. Change to no, we might not have it by the time we need it, so let's change it. I will also need to run all the cells on me, so let that run. Let the video play. Oh, it's buffering. Go back a bit.
eventually when it comes out of beta, there are different ways to create such datasets. So we can go into the datasets module, and then we can find built-in datasets, and then also base classes for custom datasets. But if we go into here, image folder, there's another parameter I'd like to show you, and this is going to be universal across many of your different data types, is the transform parameter. Now, the transform parameter is a parameter we can use to pass in some transforms on our data. So when we load our datasets from image folder, it performs a transform on those data samples that we've sent in here as the target data folder. Now, this
so it's a function that we need to give it.
is a lot more easier to understand through illustration rather than just talking about it. So let's create a transform. And the main transform we're going to be doing is transforming our data, and we're turning it into tensors. So let's see what that looks like. So I'm just going to re-import all of the main libraries that we're going to use. So from torch utils.data, let's import data loader. And we're going to import from Torch Vision. I'm going to import data sets, and I'm also going to import transforms. Beautiful. And I'm going to create another little heading here. This is going to be 3.1, transforming data with torchvision.transform. So the main transform we're looking to here is turning our images from JPEGs. If we go into train and then we go into any folder, we've got JPEG images. And we want to turn these into tensor representation. So there's some pizza there. We'll get out of this. Let's see what we can do. How about we create a transform here, write a transform for image, and let's start off by calling it data transform. And I'm going to show you how we can combine a few transforms together. If you want to combine transforms together, you can use transforms.compose. You can also use nn.sequential to combine transforms. But we're going to stick with transforms.compose for now. And it takes a list. And so let's just run out 3 transforms to begin with, and then we can talk about them after we do so. So we want to resize our images to 6464. Now, why might we do this? Well, do you recall in the last section, computer vision, we used the TinyVGG architecture? And what size were the images that the TinyVGG architecture took? Well, we replicated the CNN website version, or the CNN Explainer website version, and they took images of size 6464. So perhaps we want to leverage that computer vision model later on. So we're going to resize our images to 6464. And then we're going to create another transform.
All right.
And so this is, I just want to highlight how transforms can help you manipulate your data in a certain way. So if we wanted to flip the images, which is a form of data augmentation, in other words, artificially increasing the diversity of our dataset, we can flip the images randomly on the horizontal. So transforms.random horizontal flip. And I'm going to put a probability in here of p equals 0.5. So that means 50% of the time, if an image goes through this transform pipeline, it will get flipped on the horizontal axis. As I said, this makes a lot more sense when we visualize it. So
We get flipped on the horizontal axis. Get flipped on the horizontal axis, the 2D image will just be aligned, right? And maybe I'm thinking in 3D or something. Yeah, I'll have to see it.
we're going to do that very shortly. And finally, we're going to turn the image into a torch tensor.
Oh, maybe it just gets turned upside down.
So we can do this with transforms.toTensor. And now, where might you find such transforms? So this transform here says toTensor. If we have a look at the doc string, we've got convert a pill image, which is what we're working with right now, or a NumPy array to a tensor. This transform does not support torch script. If you'd like to find out what that is, I'd like to read the documentation for that.
What is torch script? intermediate representation of a Pytorch model. Okay.
It's essentially turning your
So basically, it's something like Torch on steroids, something like that.
Pytorch code into a Python script. It converts a pill image or a NumPy array from height, width, color channels in the range 0 to 255, which is what our values are up here. They're from 0 to 255, red, green, blue, to a torch float tensor of shape, color channels, height, width in the range 0 to 1. So it will take our tensor values here, or our NumPy array values, from 0 to 255 and convert them into a torch tensor in the range 0 to 1. We're going to see this later on in action.
0 to 1, sorry, what?
To a torch float tensor of shape, color channels, height, width in the range 0 to 1.
Okay.
So it will take our tensor values here, or our NumPy array values, from 0 to 255 and convert them into a torch tensor in the range 0 to 1. We're going to see this later on in action. But this is our first transform. So we can pass data through that.
Wait, okay, I understood what the function does, but then this is a 0 to 1.
0 to 1. So it will take
in
our
the range,
NumPy
okay,
array
wait.
from height, width, color channels in the range 0 to 255, which is what our values are up here. They're from 0 to 255, red, green, and blue, to a torch
Right.
float tensor of shape, color channels, height, width in the range 0 to 1.
So it turns it into a black and white image? Is that? We'll have to see.
So it will take our tensor values here, or our NumPy array values, from 0 to 255 and convert them into a torch tensor in the range 0 to 1. We're going to see this later on in action. But this is our first transform. So we can pass data through that. In fact, I encourage you to try that out. See what happens when you pass in data transform. What happens when you pass it in our image as array? Image as array. Let's see what happens, eh?
Right?
Oh, image should be pill image, got class NumPy array. What if we just pass in our straight up image? So this is a pill image. There we go. Beautiful. So if we look at the shape of this, what do we get? 3, 64, 64. There's 64. And what if we wanted to change this to 224, which is another common value?
So it gets turned into 3, 64, 64. So it even resized the image for us.
Value for computer vision models, 224, 224. Do you see how powerful this is? This little transforms module, the Torch Vision library.
Yeah.
We'll change that back to 64, 64.
It
And if we have
abstracts a lot of the other core array, doesn't it?
a look at what D type of our transform tensor is, we get torch float 32. Beautiful. So now we've got a way to transform our images into tensors. And so, but we're still only doing this with one image. How about we progress towards doing it for every image in our data folder here? But before we do that, I'd like to visualize what this looks like. So in the next video, let's write some code to visualize what it looks like to transform multiple images at a time. And I think it'd be a good idea to compare the transform that we're doing to the original image. So I'll see you in the next video. Let's write some visualization code. Let's now follow our Data Explorer's motto of visualizing our transformed images. So we saw what it looks like to pass one image through a data transform. And if we wanted to find more documentation on Torch Vision transforms, where could we go? There's a lot of these. So transforming and augmenting images, this is actually going to be your extra curriculum for this video. So transforms are common image transformations available in the transforms module. They can be chained together using compose, which is what we've already done. Beautiful. And so if you'd like to go through all of these, there's a whole bunch of different transforms that you can do, including some data augmentation transforms. And then if you'd like to see them visually, I encourage you to check out illustration of transforms. But let's write some code to explore our own transform visually first. So I'll leave this as a link. So I'll go up here, right here, transforms help you get your images ready to be used with a model / perform data augmentation. Wonderful. So we've got a way to turn images into tensors. That's what we want for our model. We want our images as Pytorch tensors. The same goes for any other data type that you're working with. But now I'd just like to visualize what it looks like if we plot a number of transformed images. So we're going to make a function here that takes in some image paths, a transform, a number of images to transform at a time, and a random seed here because we're going to harness the power of randomness, and sometimes we want to set the seed, sometimes we don't. So we have an image path list that we've created before, which is just all of the image paths that we have of our data set. So data, pizza, steak, sushi. Now, how about we select some random image paths and then take the image from that path, run it through our data transform, and then compare the original image of what it looks like and the transformed image and what that looks like.
Okay, gotcha. What is n though? Or is it the number of color channels?
Let's give it a try, hey? So I'm going to write a doc string of what this does, and then selects random images from a path of images and loads / transforms them then plots the original versus the transformed version. So that's quite a long doc string, but that'll be enough. We can put in some stuff for the image paths, transforms, and seed. We'll just code this out. Let's go random seed. We'll create the seed. Maybe we do it if seed, random seed. Let's put that. And we'll set seed to equal none by default. That way we can, we'll see if this works, hey? If in doubt, code it out. Random image paths, and then we're going to go random sample from the image paths and the number of sample that we're going to do. So random sample is going to, this will be a list. I'll just pass in here that this is a list. So we're going to randomly sample k, which is going to be n, so 3 images from our image path list. And then we're going to go for image path. We're going to loop through the randomly sampled image paths. You know how much I love harnessing the power of randomness for visualization. So for image path in random image paths, let's open up that image using pill.
What is okay, is just the sample size. So we'll have like 6 images like in the same plot. Is that the idea? But the seed is not defined. Am I missing a space or something? Maybe this requires not sure about this one. Let's just roll with it. Let's just write the code. We'll figure it out eventually. Okay.
Image.open image path as f, and then we're going to create a figure and an axis, and we're going to create a subplot with matplotlib. So subplots, and we want it to create one row, so it goes n rows, n cols. One row and n cols equals 2, and then on the first, or the 0th axis, we're going to plot the original image. So im show, we're just going to pass it straight in f, and then if we want to go ax 0, we're going to set the title. So set title, we're going to set it to be the original. So we'll create this as an f string, original, and then new line, we'll create a size variable, and this is going to be f.size, so we're just getting the size attribute from our file. So we'll keep going, and we'll turn off the axes here. So axis, and we're going to set that to false. Now let's transform on the first axis plot. We're going to transform and plot target image. This is so that our images are going to be side by side, the original and the transformed version. So there's one thing that we're going to have to do. I'll code it out.
I see how matplotlib is really useful for this kind of stuff. Before this tutorial, I haven't actually really used matplotlib that much. I guess I may have just used it to plot a bar chart or something like that. That was a very, very long time back.
In a wrong way first. I think that'll be a good way to illustrate what's going on. F. So I'm just going to put a note here. Note, we will need to change shape for matplotlib because we're going to come back here. Because what does this do? What have we noticed that our transform does? If we check the shape here, oh, excuse me, it converts our image to color channels first. Whereas matplotlib prefers color channels last. So just keep that in mind when we're going forward. This code, I'm writing it, it will error on purpose. So transformed image, and then we're going to go ax1 as well. We're going to set the title, which is going to be transformed, and then we'll create a new line, and we'll say size is going to be transformed image.shape. Oh, probably better, yeah, we can probably go shape here. And then finally, we're going to to go ax1. We're going to turn the axis. We're going to set that to false. You can also set it to off. So you could write false or you could write off. You might see that different versions of that somewhere. And I'm going to write a super title here, which we'll see what this looks like. Class is going to be image path. So we're getting the target image path, and we're just going to get the attribute or the parent attribute and then the stem attribute from that, just like we did before, to get the class name. And then I'm going to set this to a larger font size so that we make some nice looking plots, right? If we're going to visualize our data, we might as well make our plots visually appealing. So let's plot some transformed data or transformed images. So image paths, we're going to set this to image path list, which is just the variable we have down below, which is the path list, a list containing all of our image paths. Our transform, we're going to set our transform to be equal to our data transform. So this just means that if we pass the transform in, our image is going to go through that transform and then go through all of these. It's going to be resized, it's going to be randomly horizontally flipped, and it's going to be converted to a tensor.
Right.
And then, so we're going to set that.
But where have we? Oh yeah, we have used a transformed image. Cool. In that case, let's do plot transformed images, image paths actually, image path less transform. Gonna be, what did we call it? Data transform, right? Transform. And what else was that?
Data transfer there, or data transform, sorry. And it's going to be 3, so we plot 3 images, and we'll set the seed to 42 to begin with. Let's see if this works.
Those are the default values.
Oh, what did we get wrong? We have invalid shape, as I said. I love.
Set it. I know we're gonna get an error, but I'm still gonna run it. Oh, that explains why we had that FC error. Oh yeah, that's what I intended to call. Thanks, Python. Invalid shape 3, 64, 64 for image data. So you can't... Oh yeah, because matplotlib uses color channels last, right? So in that case, see if we can figure this out by ourselves. Can permute this. Let's just open up the docs. Torch permute. So the last one should appear first. The second one, yeah, that should do it, hopefully, right? Yeah, there we go. Actually, you know what? It should be the other way around because this looks tilted. Oh, wait, what? So transformed images outputs what? We'll print this its shape right now. Okay. So we need to shift this to the last area, right? Oh, wait. Let's look at the code here. So it permitted to 201. It shifted the first element to the second place. I'm reading it wrong, aren't I? 5 went to the first place. 3 went to the last place. So why do we have 201 here? The desired ordering of dimensions. Also, this says, hey, the second dimension should come first. The last dimension should come first. 0th dimension should come second, and the first dimension should come last. That's what 201 means. In that case, for us, this should come as last. So at the end, we need 0. and we'll keep it as 1 2. Yeah, there we go. Let's also just remove the print statement that we have. Where is it? Yeah, there we go. All right,
to begin
let's
Let's see if this
continue
works.
with the tutorial.
Oh, what did we get wrong? We have invalid shape. As I said, I love seeing this error because we have seen this error many times and we know what to do with it. We know that we have to rearrange the shapes of our data in some way, shape, or form. Well, I said shape a lot there. That's all right. Let's go here, permute. This is what we have to do. We have to permute. We have to swap the order of the axes. So right now our color channels is first. So we have to bring this color channel axis, what I mentioned, to the end. So we need to shuffle these across. So 64 into here, 64 into here, and 3 on the end. We need to, in other words, turn it from color channels
We need
first
to
to color
shift
channels
this,
last. So we can do that by permuting it to have the first axis come now in the 0 dimension
just
spot,
keep
and then
as
number
it
2 is going
is.
to be in the first dimension spot, and then number 0
Oh, I guess not, because we are printing the transform shape. So
is going to be at the back end. So this is essentially going from C, H, W, and we're just changing the order to be H, W, C. So the exact same data is going to be within that tensor. We're just changing the order of the dimensions. Let's see if this works. Woohoo! Look at that. Oh, I love seeing some manipulated data. We have a class of pizza, and the original image is there, and it's 512 by 512, but then we've resized it using our transform. Notice that it's a lot more pixelated now, but that makes sense because it's only 64 pixels. Now, why might we do such a thing?
Yep.
Well, one, does this image still look like that? Well, to me, it still does, but the most important thing will be, does it look like that to our model? Does it still look like the original to our model? Now, 64 by 64, there is less information encoded in this image. So our model will be able to compute faster on images of this size. However, we may lose some performance because not as much information is encoded as the original image. Again, the size of an image is something that you can control. You can set it to be a hyperparameter. You can tune the size to see if it improves your model. But I just decided to go 64, 3 in line with the CNN Explainer website. So a little hint, we're going to be re-replicating this model that we've done before. Now you notice that our images are now the same size, 64, 3, as what the CNN Explainer model uses. So that's where I got that from. But again, you could change this to size to whatever you want. And we see, oh, we've got a stake image here, and you notice that our image has been flipped on the horizontal. So the horizontal axis, our image has just been flipped, same with this one here. So this is the power of torch transforms.
oh, okay, I see. So okay, if it was on the vertical end, it would be upside down. But since it's on the horizontal end, it's what's the other term you can use for, similar to upside down? Right and left? No, that doesn't sound right. Upside down and not right side up. Is that it? Anyway, we'll not delve into that right now. Let's just get
Now there are a
back
lot
to
more
the
transforms, as
tutorial.
I said. You can go through them here to have a look at what's going on. Illustrations of transforms is a great place. So there's resize, there's center crop. You can crop your images. You can crop 5 different locations. You can do grayscale. You can change the color, a whole bunch of different things. I'd encourage you to check this out. That's your extra curriculum for this video. But now that we've visualized the transform, this is what I hinted at before, that we're going to use this transform for when we load all of our images into a Torch dataset. So I just wanted to make sure that they had been visualized first. We're going to use our data transform in the next video when we load all of our data using a torchvision.datasets helper function. So let's give that a go. I'll see you in the next video. Have a look at that beautiful plot. We've got some original images and some transformed images. And the beautiful thing about our transformed images is that they're in tensor format, which is what we need for our model. That's what we've been slowly working towards. We've got a data set, and now we've got a way to turn it into tensors, ready for a model. So let's just visualize I'll turn the seed off here so we can look at some more random images. There we go. Okay, so we've got stake, pixelated because we're downsizing 64, 3. Same thing for this one, and it's been flipped on the horizontal. And then same thing for this pizza image, and we'll do one more to finish off. Wonderful. So that is the premise of transforms, turning our images into tensors, and also manipulating
The
those images
first
if we want to.
pizza looks like a traditional pizza from Italy.
So let's get rid of this. I'm going to make another heading. We're up to part 4 now, and this is going to be option 1. So loading image data using...
Oh, would you look at that? We have a second view on the channel right now. Hi, 2 hours just came right now, just doing a late night Pytorch session here.
image folder. And now I'm going to turn that into Markdown. And so let's go Torch Vision datasets. So recall how each one of the Torch Vision domain libraries has its own datasets module that has built-in functions for helping you load data. In this case, we have an image folder, and there's a few others here if you'd like to look into those. But an image folder, this class is going to help us load in data that is in this format, the generic image classification format. So this is a pre-built datasets function. Just like there's pre-built datasets, we can use pre-built dataset functions. Now, option 2 later on, this is a spoiler, is we're going to create our own custom version of a dataset loader, but we'll see that in a later video. So let's see how we can use image folder to load all of our custom data, our custom images, into tensors. So this is where the transform is going to come in helpful. So let's write here, we can load image classification data using, let's write the full path name, torchvision.datasets.image folder. Put that in there. Beautiful. And so let's just start it out. Use image folder to create datasets. Now, in a previous video, I hinted at the fact that we can pass a transform to our image folder class. That's going to be right here. So let's see what that looks like in practice. So from Torch Vision, I'm going to import datasets because that's where the image folder module lives. And then we can go train data equals datasets.image folder. And we're going to pass in the root, which is our trained-er, because we're going to do it for the training directory first. And then we're going to pass in a transform, which is going to be equal to our data transform. And then we're going to pass in a target transform, but we're going to leave this as none, which is the default, I believe. If we go up to here, yeah, target transform is optional. So what this means is this is going to be a transform for the data, and this is going to be a transform for the label, / target. Pytorch likes to use target, I like to use label, but that's okay. So this means that we don't need a target transform because our labels are going to be inferred by the target directory where the images live. So our pizza images are in this directory, and they're going to have a pizza because our labels are going / target. Pytorch likes to use target, I like to use label, but that's okay. So this means that we don't need a target transform because our labels are going to be inferred by the target directory where the images live. So our pizza images are in this directory, and they're going to have pizza as the label because our data set is in standard image classification format. Now, if your data set wasn't in standard image classification format, you might use a different data loader here. A lot of them will have a transform for the data. So this transform is going to run our images, whatever images are loaded from these folders, through this transform that we've created here. It's going to resize them, randomly flip them on the horizontal, and then turn them into tensors, which is exactly how we want them for our Pytorch models. And if we wanted to transform the labels in some way, shape, or form, we could pass in a target transform here. But in our case, we don't need to transform the labels. So let's now do the same thing for the test data. And so that's why I wanted to visualize our transforms in the previous videos, because otherwise we're just passing them in as a transform. So really what's going to happen behind the scenes is all of our images are going to go through these steps. And so that's what they're going to look like when we turn them into a data set. So let's create the tester here, or the test data set. The transform, we're going to transform the test data set in the same way we transformed our training data set, and we're just going to leave that like that. So let's now print out what.
So basically this is gonna take it, it's gonna create a data set for us, a transform data set. We just provided with the directory, just the directory name. It figures out the labels, the targets, and everything, and the labels and targets are the same thing in Pytorch lingo. And yeah, we get the data sets handed off to us.
What our data sets look like, train data and test data. Beautiful. So we have a data set, a torch data set, which is an image folder, and we have a number of data points. This is going to be for the training data set. We have 225, so that means about 75 images per class. And we have the root location, which is the folder we've loaded them in from, which is our training directory. We've set these two up before, trained-er and test-er. And then we have a transform here, which is a standard transform, a resize, followed by a random horizontal flip, followed by 2tensor. Then we've got basically the same.
We resize it, we flip it, and then we convert it into a tensor. In which format? In the color channel first format.
Output here for our test directory, except we have less samples there. So let's get a few little attributes from the image folder. This is one of the benefits of using a Pytorch pre-built data loader, or dataset loader, is that it comes with a fair few attributes. So we could go to the documentation, find this out from in here, inherits from dataset folder, keep digging into there, or we could just come straight into Google Colab. Let's go get class names as a list. Can we go train data dot and then press tab? Beautiful. So we've got a fair few things here that are attributes. Let's have a look at classes. This is going to give us a list of the class names. Class names. This is very helpful later on. So we've got pizza, steak, sushi. We're trying to do everything with code here. So if we have this attribute of train data.classes, we can use this list later on for when we plot images straight from our dataset or make predictions on them and we want to label them. You can also get class names as a dictionary mapped to their integer index, that is. So we can go train data dot and press tab. We've got class to IDX. Let's see what this looks like. Class dict. Wonderful. So then we've got our string class names mapped to their integer. So we've got pizza is 0, steak is 1, sushi is 2. Now, this is where the target transform would come into play. If you wanted to transform these labels here in some way, shape, or form, you could pass a transform into here. And then if we keep going, let's check the lengths of what's going on. Check the lengths of our dataset.
What was that again?
Sushi is 2. Now, this is where the target transform would come into play. If you wanted to transform these labels here in some way, shape, or form, you could pass a transform into here. And then if we keep going,
let's just try that out. What was it? Target transform was the attribute name, right? Yeah, target transform. We'll just create a lambda function real quick, and we're just gonna uppercase it just to see if this works. And did that on train data, right? So That did not work. Try, let's see. Target transform. Pytorch. We need an example. Example image folder. Target transform, a function slash transform that takes in the target and transforms it. But why isn't it doing so here? Maybe you know what, we'll just add s and return that instead. Hopefully that works. Is it written here though? Target transform. Oh, okay, yeah, it just says lambda function. Oh, do we need to pass it as a... Oh, we need to... I think we need to use a transforms.compose for this thing to work. Transform compose. Okay, we're just gonna do transforms dot... There's quite a lot, isn't there? Transform string pytorch. And nope, not how to convert. Can we just pass it a lambda function? Maybe if we search for target classes transform images Pytorch. Let's see if there's a target transform mentioned here. No, it isn't. Transforms dot compose. I'm not sure if this would work, but it's worth a try. And I'm missing something? No, yeah. Wasn't... Oh, okay. That's why the other bracket was 4. Hmm. Okay, maybe we'll just leave that there for the time being. Let's just get back to the tutorial.
The length of what's going on. Check the length of our data set. So we've seen this before, but this is going to just give us how many samples that we have. Length, train data, length. Steak is 1, sushi is 2. Now, this is where the target transform would come into play. If you wanted to transform these labels here in some way, shape, or form, you could pass the transform into here. And then if we keep going, let's check the length of what's going on. Check the length of our data set. So we've seen this before, but this is going to just give us how many samples that we have. Length, train data, length, test data. Beautiful. And then, of course, if you'd like to explore more attributes, you can go train data dot. And then we've got a few other things: functions, images, loader, samples, targets. If you wanted to just see the images, you can go dot samples. If you wanted to see just the labels, you can go dot targets. This is going to be all about labels. Look at that. And I believe they're going to be in order. So we're going to have 0, 0, 0, 1, 1, 1, 2, 2, 2. And then if we wanted to have a look, let's say we have a look at the first sample, hey? We have data, pizza, steak, sushi, train, pizza. There's the image path, and it's a label 0 for pizza. Wonderful. So now we've done that, how about we've been visualizing this whole time. So let's keep up that trend, and let's visualize a sample and a label from the train data dataset. So in this video, we've used image folder to load our images into tensors. And because our data is already in standard image classification format, we can use one of TorchVision.dataset's pre-built functions. So let's do some more visualization in the next video. I'll see you there. Welcome back. In the last video, we used datasets.image folder to turn all of our image data into tensors. And we did that with the help of our data transform, which is a little pipeline up here to take in some data, or specifically an image, resize it to a value that we've set, in our case 6464, randomly flip it along the horizontal. We don't necessarily need this, but I just put that in there to indicate what happens when you pass an image through a transforms pipeline. And then, most importantly, we've turned our images into a Torch tensor. So that means that our data, our custom data set, this is so exciting, is now compatible to be used with a Pytorch model. So let's keep pushing forward. We're not finished yet. We're going to visualize some samples from the train data dataset. So how can we do this? We can index on the train data dataset to get a single image and a label. So if we go, can we do train data 0? What does that give us? Okay, so this is going to give us an image tensor and its associated label. In this case, it's an image of pizza, because why? Its associated label is pizza. So let's take the 0th 0. So this is going to be our image, and the label is going to be train data 0, and we're just going to get the first. The 0th 0. So this is going to be our image, and the label is going to be train data 0, and we're just going to get. So let's take the 0th 0. So this is going to be our image, and the label is going to be train data 0, and we're just going to get the first index item there, which is going to be 1. And then if we have a look at them separately, image and label, beautiful.
Yes, we can do image.
So now one of our target images is in tensor format, exactly how we want it, and its label is in numeric format as well, which is.
Wait, let's look at the train data here. We have tensor and a label. So why can't we just do image comma label is equal to, that should work, right? And yeah, of course, tell me what the label is. That worked.
Which is also exactly how we want it. And then if we want to convert this back to a non-label, we can go class names and index on that, and we see pizza. And I mean, non-label is in non-numeric. We can get it back to string format, which is human understandable. We can just index on class names. So let's print out some information about what's going on here. Print f, we're going to go image tensor. I love f strings if you haven't noticed yet. Image tensor, and we're going to set in new line. We're going to pass it in our image, which is just the image that we've got here.
I love f strings.
Then we'll print in some more information about that. This is still all becoming one with the data, right? We're slowly finding out information about our data set, so that if errors arise later on, we can go, our image, or we're getting a shape error, and I know our images are of this shape, or we're getting a data type error, which is why I've got the .d type here, and that might be why we're getting a data type issue. So let's do one more with the image label. Label. Oh, well, actually, we'll do one more. We'll do print. We'll get the label data type as well. Label. This will be important to take note of later on. Type. As I said, 3 big issues: shape mismatch, device mismatch, and data type mismatch. Can we get the type of our label? Beautiful. So we've got our image tensor. Device mismatch, and data type mismatch. Can we get the type of our label? Beautiful. So we've got
What happened here? Oh, it's supposed to be just D-typed, isn't it? There you go.
we've got our image tensor, and we've got its shape. It's of torch size 364/64. That's exactly how we want it. The data type is torch float 32, which is the default data type in Pytorch. Our image label is 0, and the label data type is of integer. So let's try and plot this and see what it looks like, hey, using matplotlib. So first of all, what do we have to do? Well, we have to rearrange the order of dimensions. In other words, matplotlib likes color channels last. So let's see what this looks like. We've got image permute. We've done this before. Image.permute 1, 2, 0 means we're reordering the dimensions. 0 would usually be here, except that we've taken the 0th dimension, the color channels, and put it on the end and shuffled the other 2 forward. So let's now print out different shapes. I love printing out the change in shapes. Helps me really understand what's going on. Because sometimes I look at a line like this and it doesn't really help me. But if I print out something of what the shapes were originally and what they changed to, well, hey, that's a big help. That's what Jupyter Notebooks are all about, right? So this is going to be color channels first, height, width. And depending on what data you're using, if you're not using images, if you're using text, still knowing the shape of your data is a very good thing. We're going to go image permute.shape, and this should be, everything going right, is height, width, color channels on the end here. And we're just going to plot the image. Can never get enough plotting practice. Plot the image. We're going to go plt.figure. We'll pass in fig size equals 10, 7. And then we're going to go plt.imshow. We'll pass in the permuted image underscore permute, and then we'll turn off the axes, and we will set the title to be class names, and we're going to index on the label just as we did before, and we're going to set the font size equal to 14, so it's nice and big. Here we go.
1 second.
Class names, and we're going to index on the label just as we did before, and we're going to set the font size equal to 14, so it's nice and big. Here we go. Beautiful. There is our image of pizza. It is very pixelated because we're going from about 512, is the original size, 512 by 512 to 6464. I would encourage you to try this out. Potentially you could use a different image here. So we've indexed on sample 0. Maybe you want to change this to just be a random image and go through these steps here. And then if you'd like to see different transforms, I'd also encourage you to try changing this out, our transform pipeline here. Maybe increase the size and see what it looks like. And if you're feeling really adventurous, you can go into Torch Vision and look at the transforms library here and then try one of these and see what it does to our images. But we're going to keep pushing forward. We are going to look at another way. Or actually, I think for completeness, let's now turn, we've got a data set. We wrote up here before that we wanted to turn our images into a data set and then subsequently a Torch Utils data loader. So we've done this before by batching our images or batching our data that we've been working with. So I'd encourage you to give this a shot yourself. Try to go through the next video and create a train data loader using our train data, wherever that is, train data, and a test data loader using our test data. So give that a shot and we'll do it together in the next video. We'll turn our data sets into data loaders. Welcome back. How'd you go? In the last video, I issued you the challenge to turn our data sets into data loaders. So let's do that together now. I hope you gave it a shot. That's the best way to practice. So turn loaded images into data loaders. So we're still adhering to our Pytorch workflow here. We've got a custom data set. We found a way to turn it into tensors in the form of data sets, and now we're going to turn it into a data loader so we can turn our data sets into iterables or batchify our data. So let's write down here. A data loader is going to help us turn our data sets into iterables. And we can customize the batch size, write this down, so our model can see batch size images at a time. So this is very important. As we touched on in the last section, computer vision, we created batch size because if we had 100,000 images, chances are if they were all in one data set, there's 100,000 images in the Food 101 data set, we're only working with about 200. If we try to load all 100,000 in one hit, chances are our hardware may run out of memory. And so that's why we batchify our images. So if we have a look at this, NVIDIA SMI, our GPU only has 16 gigabytes. I'm using a Tesla T4 right now. Well, it has about 15 gigabytes of memory. So if we try to load 100,000 images into that, whilst also computing on them with a Pytorch model, potentially we're going to run out of memory and run into issues. So instead, we can turn them into a data loader so that our model looks at 32 images at a time and can leverage all of the memory that it has rather than running out of memory. So let's turn our train and test data sets into data loaders. Turn train and test data sets into data loaders. Now, this is not just for image data. This is for all kinds of data in Pytorch. Images, text, audio, you name it. So import data loader. Then we're going to create a train data loader. We're going to set it equal to data loader. We're going to pass in a data set. So let's set this to train data. Let's set the batch size. What should we set the batch size to? I'm going to come up here and set it as a capital variable. I'm going to use 32 because 32 is a good batch size. So we'll go 32. Or actually, let's start small. Let's just start with a batch size of 1 and see what happens. Batch size 1.
Well, I was about to say it was always multiples of or powers of 2 rather. But yeah, I set it to 1. I guess 1 is I mean, not guess, 1 is a power of 2 raised to 0 as any number raised to 0 is 1. Enough of me purging out math. Let me just let's just continue with the code. Oops. Yeah.
One, number of workers. So this parameter is going to be, this is an important one, I'm going to, I potentially have covered it before, but I'm going to introduce it again. Is this going to be how many cores or how many CPU cores that is used to load your data? So the higher the better usually, and you can set this via OS CPU count, which will count how many CPUs your compute hardware has. So I'll just show you how this works. Import OS, and this is a Python OS module. We can do CPU count to find out how many CPUs our Google Colab instance has. Mine has 2. Your number may vary, but I believe most Colab instances have 2 CPUs. If you're running this on your local machine, you may have more. If you're running it on dedicated deep learning hardware, you may even have even more, right? So generally, if you set this to 1, it will use 1 CPU core, but if you set it to os.cpu count, it will use as many as possible. So we're just going to leave this as 1 right now. You can customize this to however you want. And I'm going to shuffle the training data because I don't want my model to recognize any order in the training data, so I'm going to mix it up. And then I'm going to create the test data loader. Dataset equals.
And now we use shuffle. Alright, let's use shuffle. This shuffle thing costed me like the entirety of yesterday's stream. And yeah, if Daniel is using it, we'll use it. Because if there's one thing that we learned from yesterday's stream, it is to always follow the tutorial as it is. Maybe not always as it is, but you know, try to keep it as it is most of the times, and you can always experiment later on. I'm not saying experimenting is bad. You need to experiment to learn. Anyhow,
test data and batch size equals 1. Num workers, I'm going to set this to equal 1 as well. Again, you can customize each of these. They're hyper.
then why do we have that constant if you're just gonna assign it 1? Use the constant.
Parameters to whatever you want. Number of workers, generally the more the better. And then I'm going to set shuffle equals false for the test data, so that if we want to evaluate our models later on, our test data set is always in the same order.
Alright, so yeah. This is what I messed out last time. Anyhow. I was gonna say that to true. Okay,
so now let's have a look at train data loader, see what happens, and test data loader. Wonderful. So we get 2 instances of torch utils.data.data loader, and now we can see if we can visualize something from the train data loader as well as the test data loader. Or actually, maybe we just visualize something from one of them, so we're not just double handling.
Well, I misspelled shuffle.
Everything. Do we get a length here? Wonderful, because we're using a batch size of 1, our length
Oh, okay, that's not what I meant.
of our data loaders are the same as our data sets. Now, of course, this would change if we set, we didn't even set this to the batch size parameter. Batch size, let's come down here and do the same here.
Okay.
Batch size. So we'll watch this change. If we wanted to look at 32 images at a time, we definitely could do that. So now we have 8 batches, because 225 divided by 32 equals roughly 8. And then 75 divided by 32 also equals roughly 3. And remember, these numbers are going to be rounded if there are some overlaps. So let's get rid of, we'll change this back to 1. And we'll keep that there. We'll get rid of these 2. And let's see what it looks like to plot an image from our data loader. Or at least have a look at it. Check out the shapes. That's really the most important point at this time. We've already plotted enough things. So let's iterate through our train data loader. And we'll grab the next one. We'll grab the image and the label. And we're going to print out here. So batch size will now be 1. You can change the batch size if you like. This is just, again, another way of getting familiar with the shapes of our data. So image shape. Let's go image.shape. And we're going to write down here, this shape is going to be batch size. This is what our data loader is going to add to our images. It's going to add a batch dimension. Color channels, height, width, and then print. Let's check out the label shape. Same thing with the labels. It's going to add a batch dimension. Label, and let's see what happens. Oh, we forgot.
a label a label has a shape. I mean, it's an individual, right? Or maybe because we give it gave it into a data loader, maybe gave it
We've got the end
into
of
the
the
data loader.
Beautiful. So we've got image shape. Our label shape is only 1 because we have a batch size of 1. And so now we've got batch size 1, color channels 3, height, width. And if we change this to 32, what do you think is going to happen? We get a batch size of 32, still 3 color
Oh, okay. That's why it has a label has a shape, because usually you don't create batches of one images, right? That that's beside the point of why someone would probably use data loader.
channels, still 64, and now we have 32 labels. So that means within each batch, we have 32 images and we have 32 labels. We could use this with a model. I'm going to change this back to 1. And I think we've covered enough in terms of loading our datasets. How cool is this? We've come a long way. We've downloaded a custom dataset. We loaded it into a dataset using image folder, turned it into tensors using our data transform, and now batchified our custom dataset in data loaders. We've used these with models before. So if you wanted to, you could go right ahead and build a convolutional neural network to try and find patterns in our image tensors. But in the next video, let's pretend we didn't have this data loader, this image folder class available to us. How could we load our image dataset so that it's compatible, like our image dataset here? How could we replicate this image folder class so that we could use it with a data loader? Because data loader is part of Torch utils.data. You're going to see these everywhere. Let's pretend we didn't have the Torch vision.datasets image folder helper function. And we'll see in the next video how we can replicate that functionality. I'll see you there. Welcome.
All right, I think this is a good time to end the stream and the today's session of Pytorch. And yeah, we have covered almost 2 hours worth of content, and I'm happy with what we learned today. We learned about how we can transform our data, and yeah, excited to make this pizza sushi steak recognizer tool. I think this project, this is gonna be our first. I guess if you consider the MNIST and I don't know, can you consider them as projects? I'll consider this as a project though. Anyhow, so yeah, I'll see you in the next one is all I have to say. All right, cheers. Let's see what all exciting things we learn in the next stream. See you in the next one, and take care.